Here's another example series. The sum as n goes from 1 to infinity of 3n squared over n cubed plus 1. Does this series converge or diverge? And does it converge absolutely? Well, we could try the ratio test. Notice, by the way, all the terms of this series are positive. So there's no question of converging conditionally. This series either converges absolutely or not at all. Let's try it. Let's find the limit as n goes to infinity of the absolute value of an plus 1 over an. And that is the limit as n goes to infinity of, again, we're going to have this big fraction here. What I might do is immediately from the get-go, instead of taking a fraction divided by a fraction, I will take the top fraction and multiply by the reciprocal, the bottom fraction, right at the beginning, so I can save myself space and frustration. So, an plus 1 means I should take the expression for an and replace all the n's with n plus 1. So we're going to have 3n plus 1 squared, put those parentheses there, over, we had n cubed, now it's n plus 1 cubed, plus 1. Now, instead of dividing by an, I'm going to multiply by the reciprocal of an. So I'll just take the an and I'll just flip that. So we have n cubed plus 1 over 3n squared. And that's it. Absolute value. So, now we just need to simplify this expression and see what the result is. This equals the limit as n goes to infinity. First thing that I'm going to note is that every expression that we are multiplying or dividing by in here, all of the factors of this thing are all positive. N is large and is approaching infinity, say n is 100 million. Each of these things is positive. So the absolute value is actually not doing anything here. So I'm going to drop the absolute value signs right away. And we're going to have 3 times n plus 1 squared times n cubed plus 1. And that will get divided by n plus 1 cubed plus 1 times 3n squared. So, we just have a rational function here, a polynomial over a polynomial. I'm not going to waste your time and mine showing you the steps of how to multiply these by hand, and we'll just write out the answer. So if we expand these polynomials on the top and bottom out, we'll end up with 3n to the 5th plus 6n to the 4th, yada, yada, yada on the top, and another 3n to the 5th, etc. on the bottom. Not worth going into the trouble of how we actually expand those. In fact, you don't even need to really expand these because we know the important question is what is the highest degree term on the top and what is the highest degree term on the bottom. And you can actually figure that out from looking at the initial unexpanded rational function. So on the top we have 3 times n plus 1 squared. That means we're going to have an n that's being squared. And times n cubed, so you're going to multiply by n cubed. That's going to give you n to the 5th times 3. On the bottom, we're going to have an n plus 1 cubed, which means the highest degree term there is n cubed. And then that gets multiplied by 3n squared, so we'll end up with 3n to the 5th on the bottom as well. Either way you slice it, in the end, what we have is a limit as n goes to infinity of a rational function whose highest degree terms on the top and bottom are both 3n to the 5th. What that tells us is that that limit is going to be 1. What do we conclude from this? Well, the ratio test tells us we should compute this limit of each term divided by the previous term, and if we get 1, then the ratio test actually doesn't tell us anything. We cannot draw a conclusion. This is going to happen in general if you have a series whose terms are given by a rational function, or in fact any algebraic function. You could have square roots in there or other kinds of roots in there. You could have exponents, constant exponents, addition, subtraction, multiplication, division. And as long as the function that describes the terms is algebraic, when you compute this limit that's involved in the ratio test, you'll always end up with just 1 for that limit. Which means the ratio test is not helpful in cases where the function that describes the terms is algebraic. It's really only helpful if there is some kind of faster growing function in there, such as an exponential function or a factorial. Then the ratio test is likely to give you some kind of answer, but not in this case. So what should we do? Well, let's actually try a different test. Since we didn't get a good answer from the ratio test, we'll need a different test, and a good strategy in this case, especially when you have a series whose terms are given by an algebraic function of any sort, is to try the comparison tests by comparing to a p-series. In fact, usually the easier comparison test to do is the limit comparison test. So let's compare to a p-series. In fact, if I look at the expression that describes these terms here, if I just ignore that plus 1, and in fact ignore the 3 as well, n squared over n cubed is 1 over n. So let's try this p-series, the sum, as n goes from 1 to infinity, of 1 over n. Now, this is the harmonic series. This diverges. So let's try the limit comparison test with this series, and we suspect that this series is, and we suspect we're going to get a conclusive answer that our series does the same thing as the harmonic series, which diverges. Let's try it. Let's take the limit as n goes to infinity of an over bn, where an is the terms of our original series, and bn is the terms of the series we're comparing to. So, this time we're going to have the limit as n goes to infinity of 3n squared over n cubed plus 1 over, big division bar, 1 over n. Now notice that in both of these tests, the ratio test and the limit comparison test, we are taking a ratio of terms of some series. But we are doing two entirely different ratios. In the ratio test, it was the ratio of a particular term of the series we care about divided by the previous term of the same series. And that was giving us something that's kind of equivalent to the common ratio in a geometric series, and seeing what happens with that. In this case, we're looking at the ratio of a particular term of the series we care about divided by the corresponding term of an entirely new series. So we are looking at two entirely different ratios, and we will draw different conclusions from those. Let's actually finish computing this limit here and see what we get. So we have the limit as n goes to infinity of 3n squared over n cubed plus 1. And again, instead of dividing by 1 over n, I could have right from the beginning said times n over 1. So we get the limit as n goes to infinity of, let's see, 3n squared times n is 3n cubed over n cubed plus 1. The interesting thing here is that this ratio test, because we made a particular choice of what series to compare to, namely the harmonic series, the series with the sum of 1 over n, we end up with a limit of a rational function where, again, the powers on n, on the top and bottom, are the same. The degree of the top and bottom are the same. Now, we could have chosen to compare to a different series, but the only one that's actually going to be useful to us is the one where the degree on the top and bottom end up the same, because dividing by 1 over n is equivalent to multiplying the top by n, and we end up with n cubed over n cubed. So this limit is going to end up being 3. Now, what do we conclude from this? Remember, we are using the limit comparison test this time and not the ratio test, so the rules for what conclusion we draw are entirely different. The limit comparison test says if we take the limit of the nth term of one series over the nth term of another series as n goes to infinity, if we get any finite result that is not 0, any finite number greater than 0, then we know that both series have the same behavior. That is, if the series we're comparing to converges, then our series converges. And if the series we're comparing to diverges, then our series diverges. So since this is finite and greater than 0, and since the harmonic series that we're comparing to diverges, we know that our series also diverges. And we're done.